Okay, so let's continue. We did a little bit of binary conversions. So let's talk a little bit more technical. All right, so overflow. Overflow is because we have a limited amount of space. So if I have 8 positions and I have 8 positions, so I have a byte and I can fill it up with ones, then I'm gonna get to 255, right? So it's like 1, 2, 4, 8, 16, 32, 64, 128. So this one is 128. And then if I sum all these up, is 127. So altogether is 255. Because the next one in the order is 256, right? So to represent 256, I would need one extra bit. So then if I have 255 and I add one more, I don't have enough space. So I have an overflow, right? So overflow is the property of us using kind of a positional decimal system. And then we have the overflow of the integer. Another overflow is when we have a memory, continuous memory allocated, like a buffer. And then I have a buffer kind of certain length. And then I write something which goes beyond that length. So I'm overwriting memory, which is sort of beside that buffer. And it's called memory overflow. But it's a kind of a different concept, right? Okay, so then what are you programming in? What are your languages of choice? So in this course, we will learn a little bit of Solidity. Solidity is very similar to JavaScript. It's sort of derived from JavaScript syntax. So people who know JavaScript will feel kind of a little bit at home here. In Jovic, when we have a programming degree, we start with C, then students have C++, then students have Golang and Haskell for functional programming, and Rust. JavaScript and Python, we don't really teach, but we expect students to learn on the go. So we sort of let them study on their own, but they learn a number of languages to sort of expose them to different programming paradigms and also different concepts. So like, for example, those languages don't have concept of memory management. Java neither, but at least Java has like pointers. These languages don't have pointers. So to learn about pointers and memory alignment, you have to learn C++. Java has pointers, but it has garbage collector. So it means the runtime system is managing memory. Like you, as a programmer, you don't have to manage memory yourself. But with C, C++, or with Rust, you have to. So those are kind of manual memory managed languages. And those ones are where the memory is managed for you by the runtime system of the language. So it kind of depends, like what you know and how you're using it to sort of learn those different patterns. And then Haskell and F#, those are examples of functional programming paradigm. It exists in other languages as well. You can do some functional patterns and design patterns in JavaScript, but it's sort of easier to learn them using a functional language. And then functional languages have some certain properties, like Haskell, for example, is lazy. So it's very easy to deal with infinite collections or infinite things because it does not evaluate everything on the fly. So in some programming languages, you cannot say A is an array from 1 to infinity, right? In some languages, you can say it, like A goes from 1 to infinity, but in some languages, you cannot. You have to say, like, how big is A? Like, I need to know. Like, is it 10 numbers or like, you have to tell me. And it's like, If the language is lazy, you can say, no, no, we don't care. It goes all the way to infinity, right? All right, so Git, okay. Git add. We technically don't have to learn Git in this course. And I don't think we will, but if you want to use some of your time and you are not super familiar with Git, then I encourage you to sort of like learn the basics. So Git add is adding stuff to the stage zone, and then it will be staged for the next commit. So you're kind of adding things to the staging zone. All right. And then which command saves the stage? You don't see this yet. So Git is quite convenient for us to share information. So if I have some like examples, or if I have something to share with you, I can share it via Canvas as a sort of a zip file, right? So I can do this. But then if I did some changes, I have to share another zip file, right? And say, oh yeah, this one is deprecated, now use this one. If we use Git, then it's sort of easy to see stuff like in real time. Like every time something changes, then you sort of see it. So which command saves stage changes? It's the commit. So Git commit pushes stuff from the stage zone into the actual Git repository. And then one more. Yeah. So those who know, they know. So Git pull. Git is a distributed version control system. So you have multiple repositories. So you have one repository, another repository, and you can have another one. If this one is, let's say, a GitHub, people say, okay, GitHub is like a special thing because if I have Bob and Alice and they kind of work on some code base, they say, okay, let's agree that GitHub is our sort of a common repository. So they will be pulling and pushing from this one to kind of communicate the changes such they don't have to communicate directly, right? But they could, like you can say, yeah, I have like I open port, SSH port or something, and you can kind of push and pull from me directly, and this is allowed in Git. Like it doesn't have this hierarchical setup built in. It's just an agreement that GitHub is the sort of like origin. And we usually designate an origin for the one which is like the main one. And then people kind of clone the origin and then do changes and then push the changes over there. So you're pulling and pushing. And then you're doing adding like locally. If you have some changes, then you would add them to the staging zone, then you will commit. And then they will be committed locally. So you kind of version controlling your stuff locally. And then from time to time, if you have a release or if you want to communicate with Alice, you would push your changes there. So here you do pull or push or fetch this one or this way, and Alice is doing the same. And locally you're doing Git adding and committing. There is also branching, so you can have local branches or branches pushed to the remote repository. So it's not really like rocket science. It's kind of, again, kind of a number of simple concepts, but it is kind of useful. So as I say, like if you can dedicate a little bit of time, those of you who don't use it, please do. So then there is it a quiz? Yes. So there is one more question about Git. Correct. So Git checkout changes the branch you are in. So branches are sort of like kind of how to use a metaphor. It's sort of like a workspace. So you have your code and like you're working on it, but you say, oh, yeah, I want to try something out. So then you sort of changing to a different zone. You're like making a copy of everything. You're playing with something and say, ah, now discard it. I'm back to this one. So it's sort of like a branch. And checkout sort of allows you to switch from one branch to another, but with B, it kind of creates a new one and switches to it. So Git is sometimes criticized by having a very non-intuitive user interface. So people often have certain expectations of how it works, and it's a little bit confusing. And you can see it here. Like, why would you say, like, to switch to an existing branch, you use checkout, but to create a new branch, you're doing checkout -b. Like, it's a little bit like weird from usability point of view. But the thing is that Git was not like who created Git? Do you know? Yeah, Linus. Yeah, the same guy who created Freaks. So he is a little bit like opinionated, and his main idea was not to create like if you're building a system. So if you are like a developer and you're building a system, so normally it's like you're building a system and then you have a user and then you have this sort of like UX for the user such that the UX is part of the system, right? And the user is sort of interacting with the system through whatever the UX kind of creates, right? And Git has the same, like you have, I don't use them, but there are some like UI applications which hide the Git behind the UI and the user interacts with this UI, right? So you have a certain like logical interaction with the UI and then like Git is here, right? And then it sort of works, but I don't do it. And many people who use Git, they don't like it neither. Like they feel this UI like misses the point. Misses the point. And when Linus created Git, he sort of didn't care about this and didn't care about the user. He cared about the interface of how this works and how you can control it, right? So the focus was on this interface here, not on the UI. And the commands are basically a reflection of how Git is constructed inside, how it works. So that's how the commands work. And then a user kind of interacts with the core, like it actually, you interact with the internals of the Git, right? So they are not hidden from you, they are sort of exposed to you via those commands. And then if you kind of say, oh, no, it's too much for me, I want to have a UI, you kind of UX, then you would kind of do a translation layer between the user of the user intent and this. So you have a certain workflow in mind, and then this UX would kind of help you with that particular workflow, right? But if you're interacting with this natively, you're sort of exposed to the internals. And many people say, yeah, that's how it was intended and that's how it should be because it opens up the possibility. Like you can use it the way you really want. There are infinite possibilities of how you can kind of interact with it. If you shield it with the UX, you're kind of limiting the use cases, right? All right, so then some questions about DevOps. So what is a virtual machine? You had the cloud computing course, right? So you know about virtualization, type 1, type 2, or you don't? Okay, so very quick. If you have a machine, so if you have a machine of a certain architecture, let's say I have a machine of x86, and now I have a CPU, which like Intel CPU, which is offering me that machine. I can have a virtualization layer which is already on the CPU. And that virtualization layer allows me to share this resource between, so then on top of that, I have the operating system. And then on top of the operating system, I have sort of application layer. So applications talk through the operating system, but the operating system does not talk to my CPU directly. It kind of talks to the hypervisor of the CPU to get the resources like registers and kind of cycles directly, right? So then this multiplexing is different virtualization than if I have the OS presenting something to the rest of the system. Like this one, like this is the software boundary, and here is the hardware. So if the virtualization is kind of here, it's type 1. If the virtualization is down here, it's type 2. And then some virtualization is sort of taking advantage of this one as well. So then it's sort of a little bit like some type 2, they have the capability to utilize some of the capabilities of the underlying architecture, right? So then it depends on like exactly how this works. I worked in some blade servers in the data center, and then in the data center you have a machine. So you will have a CPU, you will have a power supply, you will have RAM, and then this is not directly accessible. This is accessible after what's called hypervisor, which is a hardware hypervisor, so type 1, virtualization type 1, or disk also. So then you have, on top of this hypervisor, you have a small Linux. So here you have some small Linux server, which talks to the hypervisor, and kind of navigates the architecture. And you can SSH to this Linux, and you can say, like, if you have multiple CPUs, you can say, okay, turn off CPU number 2. So make it like a fail. So like if you have CPU 0, CPU 1, it will say, okay, CPU 1 is like out. And you can say, in the bank, second row of this bank, make this RAM fail as well. So you can talk to this guy and make the hypervisor do whatever you want. And top on this thing, you actually have the operating system, right? So here you have the actual operating system like Linux or something you want to run, right? So this is the real operating system, which is kind of talking to this guy to get access to the hardware and so on. And this is virtualization type 1. And then if you have some additional virtualization layer that you're running 2 different operating systems on 2 different sort of hardware, then you would have type 2. So type 2 is here, type 1 is here, right? So the normal, like if you're using VirtualBox, it's virtualization type 2. It's done on top of the operating system, of your operating system. And you may have some acceleration, like it may go directly to your CPU, but most of the time it will just talk to your operating system for virtualization. It just presents to you that you have Intel machine on a Mac, for example, right? Okay, so any questions about this? Does that make sense? It was actually quite fun because we, for example, could tell this Linux to turn off the RAM, go to the box, open it, take this RAM out while the server is running all the time, right? Take this RAM out, replace it, and then enable it again and turn it on. Same with the power supply. We had one, like they usually have redundancy. So we had 2 power supplies. So there were 2 power supply, power 0 and power 1. power 1 failed. So we said, okay, power 1 is actually not available. It was marked as not available. Then you go, you replace it, remove it while the server is running all the time, right? So this is done for the purpose of no downtime. You want the servers to be like continuously running all the time. All right, what do we have next? Okay, some easy networking questions. And from the previous slides, we know that you are quite strong in networking, so that should be easy. Perfect. So if I have a stack, if I have the data link, I have Ethernet, then I have the IP layer, and then I have TCP layer, on which, and then I have some other layers. Let's say I have application layer. Where is the concept of port coming in play? Which ones of these has a concept of port?
TCP.
Perfect, TCP, of course. So here I have a concept of MAC address. Here I have the actual IP address, right? As the name suggests. And here I have ports, right? So ports. Good. So, okay, philosophical question. What are the benefits of decentralization? Why do we teach blockchain technology, or why do we talk about decentralization? What is the, or what's the reason? What's the motivation? Yeah, so those are good answers. So we can, so if we kind of consider, let's consider this. So one of the centralized systems that we kind of have as an example is a bank, right? So if we have a bank, and then we have money, and we have people, we have Bob and Alice, then the bank kind of stores, and we're doing electronic transfers. We're not talking cash, we're talking like digital money, right? So we have those two people. And then if Bob needs to pay Alice, it kind of needs to go, he needs to tell the bank to take money out of his account and then put into Alice's account, right? So we have privacy problems. We have dependency, like if the bank is closed, they cannot like exchange, like they cannot make payments. The privacy I already mentioned. Traceability, yes, it is traceable. I mean, the bank knows everything, right? The bank knows who paid whom, when, and so on, right? So traceability, not such a big thing. What else we have? Sharing. Yes, this one I was looking for. It's a single point of failure. So if the bank is down, or if something happens to the bank, everybody who is using the bank is screwed, right? So a central system usually has a single point of failure. If that central point fails, like everything goes to hell, right? So Bob cannot pay. So if we consider that, and we consider cash, so if you have cash now, is cash as a payment mechanism centralized or decentralized system? Yep. It is decentralized. Cash is decentralized because Bob can pay Alice at any time, without bank. And also it can do it privately, such that nobody knows about it. And it has kind of all the good properties of decentralization. How about traceability? How easy is to trace what has happened with cash? Really shit, right? You can't really trace anything, right? So traceability is much better with centralized system and much worse with decentralized system, right? With cash, what is centralized? So cash in itself is a decentralized system, but there is one element of cash that is centralized. What is it? What is it? The issuance of the initial banknotes, right? The issuance of the initial coins or cash is centralized. It's done by central bank, right? So we have concept of a central bank which generates and prints the money, right? And it's only one, like that. There is only one kind of central bank which prints the money. Once the money are printed, then the system kind of operates in a decentralized fashion, right? So normal monetary systems are kind of combination of centralization through the central bank and decentralization through cash. And then if we remove cash and we only have electronic transfers, we remove all that decentralization that existed. It will be purely centralized system, right? All right. Okay, changing gears again. What is Docker? Yeah, we're covering a lot of different topics today, jumping from a topic to topic. So what problem is Docker solving? You familiar with Docker? Did you use Docker in the cloud course? Perfect. All right. So yes, it solves the, like, it works on my computer problem and it doesn't work on yours. If we use all Docker containers, we have all the same environment. It has to work everywhere the same. Like we unified like how things are set up and how things work. Perfect. So let's see the leaderboard. How are we doing? A little bit of reshuffling, but yeah. Avind is leading the pack for now. Okay, so not a quiz question, another networking question. Which of the TCP, in the TCP model, which layer handles end-to-end communication? Okay, a little bit of so let's think about it. So I have a one computer, I have another computer. This guy is a server. This one is a browser. They are connected. So they are connected through the TCP/IP stack. So on the stack we have a MAC. So we have the Ethernet layer to a switch or something. Then we have the internet protocol. Then we have TCP. Then they are talking, like the browser is talking HTTP to get something from the server, right? So they are using some form of application protocol. Let's say they're using HTTP or HTTPS. So then in that model, who is responsible for end-to-end communication? What do you think? Ideas? Most of you said network layer, right? So most of you said the IP. So now let's think about it. So if this server is behind a firewall and has an IP of the 192.168.0.1 kind of example, and this guy, your browser, is also behind a firewall, and you also have 10.0.0.1 IP, right? You don't know that IP even, right? Like it's not end to end. So like your 10.0.0.1 does not talk to 192, right? So it cannot be network layer because your browser is not talking to that IP address. And this IP address is not responding to this IP address, right? So end to end definitely is not this one. Make sense? Yeah. So the correct answer, I guess, it's there. Yeah, it has to be the application layer, right? It has to be the actual like HTTP. Like you are setting up like who do I talk to? I talk to Microsoft.com. I actually don't know whatever the IP will be at the end, but I know that my communication is to that end, right? And then this end will talk to me initiating it. And with using some form of like bridging or some form of like, yeah, bridging. It's technically called bridges, right? To enable it. But the individual path will be kind of on the network layer or transport layer. But the end-to-end kind of happens like it has to happen above that. All right. So HTTP, an easy question. We have to be fast. Do you know HTTP codes? Yeah, some. Do you know the ranges? So 200, usually stuff is okay. 300, something on the server, like a redirect or some sort of a communication thing. 400, like you did something wrong because you're asking for a resource that does not exist. So it's sort of usually on the client side. And 500, usually something on the server side, right? So 500, internal server error. Yeah. All right. So internal server error is 500. Okay, DNS. What is DNS doing? Yep. Most of you are doing fine. So it is a translation layer between human readable names or a hierarchy of human readable names, domain names to IP addresses. It's one of the attack vectors. So it's one of the like systems which is originally designed to be hierarchical and kind of managed by national registrars. But we have some actors or even state actors that sort of making the system malfunction, which means you can get some DNS poisoning or you can get things to go wrong because the name will not resolve to the correct thing. It will kind of resolve to the malicious thing. And then your traffic will go somewhere where it not intends. So those are really hard to deal with because those attacks happen on the infrastructure. And then there are mechanisms to kind of help with this, like doing updates and doing communication with DNSs using some verifiable keys and like authentication. But as it is now, it was designed to be a little bit insecure because we shifted the security to the kind of legal obligations of the registrars. That means the technical layer was not sort of controlling it. And now we kind of need to deal with it. All right, another easy one. It's a quiz. Great, we almost done with the quizzes. So 5 more questions to go. So I don't know how it is in Christiania, but at NTNU, we have like an internal gateway, which is unauthenticated, and you can like telnet to it and talk with it directly, like because it does not like authenticate you. So SMTP is a very request response protocol, text-based, and you can basically send email via that protocol, just typing stuff like you like interacting with the socket, which is the SMTP like endpoint. So it is quite fun. Like we can, as I said, like send an email, just like typing all the sequences of messages, communication, like request response to that protocol. It's quite a simple. Most of the old style protocols, they are quite simple and text-based. So when you're submitting a form, what we usually use is about REST services. So we're using a post command from HTTP. Right. Okay, another default port. Okay, need to start that one. So we remember this one was already SSH. We remember this one, so it's out. From the remaining ones, we kind of know that this one is just a plain HTTP, so it cannot be this one. And then it sort of leaves us two. This one, what is this one? Just a typical secondary HTTP port without the security. Other ports that are typically used for like application developments apart from 8080 is like 3000 or some form of like something like this, depending what we do. And most of the crypto work that we will do is probably 3000 that we will interact with. Okay, so what is the difference between HTTPS and HTTP? Okay, so here we sort of have the term encryption. So this is what we will spend the next slide deck on. We will talk about encryption and about like what sort of protocols are being used here and like algorithms and how they work and what like why do we have them and how, like what are the properties. So we will dive a little bit deeper into the TLS and SSL to sort of understand a little bit mechanics behind it. So how are we doing with time? Yeah, I think I can finish the deck and we can have a break. So HTML. Easy. So there are multiple file formats that we use for different reasons. HTML is a special case of another format. What is that other format that HTML is a special case of? Yes, it's even in the name, right? So here it's like hypertext markup language, extendable markup language, right? So it's XML. So it's like a instance. HTML is an instantiation, like a concrete instantiation of XML. XML can have multiple instantiations, and it has a specific schema that defines the instantiation. You can define your own XML, of course, and then you will have a special schema, and then you can have your own XML kind of markup language, right? And HTML is like a concrete example of XML. They went through a couple of versions, and they tighten up the schema such that like a idiomatic way of using HTML is kind of similar to now using XML. Originally, it was a little bit loosely structured. So for example, if you say unstructured list, and then you say list element, and you set something, you didn't need to close it. And then you say another list element, then you kind of say that, and then you could do another unstructured list. But now, because of the schema verification, it would say, yeah, this is not an idiomatic HTML. You sort of should close the tags, right? And then you should, before starting a new one, you should close the previous one, right? So you should have the ending tags. So it's a little bit more enforced, and it's checked. And then we have the published schema, and you can kind of validate that the document that you got is properly formatted HTML document, right? All right. So we have some shuffling in the leaderboard. Don't give up, like, answer. All right, so we have a couple of more questions. What is a cryptographic hash function? This is super important for this course, that we understand hashing. We will come back to it. It is important enough that I want to spend a little bit of time. Yes, it is a one-way function, so all those people are fine. This one is a trivial question as well. This question. Yes. We have different names also. So there is a SHA-1. SHA-1. How many bits this one had? Yep. No. 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 128. So SHA-1 was 128. SHA-2 was 256, and now it's renamed to this one because it was a little bit confusing. And then SHA-3 is 512. So how about SHA-1? SHA-1. So we will talk about how hard it is to find a collision, but hashing functions take a document and they produce a fixed length string of 128 bits. So like SHA-1. and you cannot recover that document from this, obviously, right? The property is that you should not be able to find what this document is just from the hash. You can go from the document to the hash, but not from the hash to the document. So to go from the hash to the document, you would have to find a different document which, when hashed, produces exactly the same hash. And this is called hash collision, right? So is it possible to have a hashing function that does not have collisions? Is it theoretically possible to have a hashing function that does not have collisions? No, why not? Exactly. So on this side, we have infinite number of possibilities, and then we transform it. And on this side, we have a fixed length, which means we have to have collisions, because otherwise that wouldn't work. Like, we have many things here than here. So some multiple things have to map to the same thing here, right? So that the length of the domains does not match, which means we always have collisions. Why the collisions are a bad thing? Because we're using hashes to prove authenticity of stuff, right? So what we do is we create a document. Let's say we have a contract which says that Mariusz gonna get, I don't know, 50,000 krona as a salary. And then I sign it, and the person giving me the salary signs it, and we hash it. And then we have a hash with the signature saying, this and this has to match because this is the document, right? So now if I can find a collision, and I could potentially like change it to a different number and say, yeah, look, it is signed, the hash matches, everything is fine, I could forge the original document, right? So ability to find a collision is kind of preventing us from using the hashing for making that this is authentic. It has not been manipulated because it hashes to that hash, right? So collisions are kind of unintentional, side effect of the fact that we can hash longer things to smaller things. So we try to avoid it. So what we do is we create hashing functions which are really, really hard to find collisions. And the moment somebody comes up with a mechanism to find the collision, that means this hashing function is shit. We have to throw it out, right? And that's what happened to SHA-1. So SHA-1 is 128 bits. It has been a very popular hashing function, which worked beautifully for many years. And then, I don't remember the year, but one year, Google announced a competition saying if someone can find a collision of the particular hash, then they're gonna win something. They're gonna win some Bitcoins, okay? And somebody posted a solution and got the Bitcoins. So you have the BTC as a reward. I don't remember how many there were, like there were some BTCs. And then an anonymous person posts and gets the reward because that person has the collision, okay? But that person was not the one who found the collision. Google itself used the infrastructure to find the collision for SHA-1, and they published a paper demonstrating that they found a collision. So they basically had the document. They didn't modify the salary or anything. They just added like extra stuff, right? So it was basically the same document with some extra stuff added, which was hashing to the same hash. And they published a paper. And somebody read the paper and said, oh, great. So, and the person used that paper to claim the reward because Google didn't claim that reward themselves, right? So it was kind of a funny story. But after that incident, we had to drop using SHA-1 for anything because now we know somebody with enough money can rent like a Google infrastructure for doing a lot of GPU computations and can actually force collisions, right? Does it have like practical implications? Yes, to some extent it does. This didn't really do any malicious thing. It just demonstrated that SHA-1 is not like strong enough. So we have to use 256 now, right? So 256 bits is the minimum kind of length of hashes that we use for serious applications, because we know like 1 to 8 is sort of not enough, especially with this family of hashing functions. So what we try to do is we try to find hashing functions which are fast, but at the same time really hard to find collisions with, right? All right. This one. Yes, this one is quite easy. The distractors are quite obvious distractors. So yes, in symmetric encryption, you only have one key, and it is used for encrypting and decrypting. So that's why it's called symmetric, because you basically reusing the same key in both directions. Okay. Yeah, this one is a quiz. This one confuses people sometimes. Yeah, it confuses you as well. So we will talk a little bit about it later, but effectively you have two people. We have Alice and Bob. Okay, and Alice has a public key and a private key. Let's call them pub A and priv A. And then Bob has pub B and priv B. So obviously, private keys should not be shared. They are called private because if they are shared, like the whole thing goes to hell, right? So private key of Alice is only known to Alice. If Alice shares it with anybody, then it does not work anymore. So, but the public keys are shared. So these ones are kind of a common knowledge. So both of them know both of those keys, right? So now if Bob has a message, and he wants to send it such that only Alice can read it, right? That means Alice has to know something nobody else knows to be able to decrypt it. So to encrypt this, Bob will have to use Alice's public key such that she will use the private key to decrypt it, right? That makes sense. So the correct answer here is when messages from Bob to Alice, Bob has to use Alice's public key. Then Bob also might want to prove that the message is not manipulated, right? So he will calculate the hash and he will sign the hash with his which key? If he wants to sign it. So for signing, sign. So this one was for encrypt. Was he uses her public key. But when he wants to sign the message, such that when she gets the message, she can verify that it has not been manipulated, that it was actually written by Bob. Which key he is using for signing? Which one? Say it again. Private key. So he will use his private key to sign it, and she will use his public key to verify it, right? So here is to sign. So this one is to encrypt, and she uses this one for decrypt. Yep, makes sense. Otherwise, that like any other combination does not make sense because those two keys are private, right? But it is a bit confusing. So it kind of confuses people sometimes. Right. So signature. Yeah. What do we use signatures for? Yes, I just said this. So we're using it for authenticity and verifiability of that message, that it hasn't been manipulated. It has not been like obtained by man in the middle and changed and passed to the recipient and so on. So it's authentic and not manipulated. Right. We're getting there. We're getting there. Yeah, so I think I have 8 more slides. Maybe you should have a break before I go through those slides. So let's keep that one as a last one. So a blockchain is best described as it is a peer-to-peer system, but it does not really allow you to share files. Like it shares something, but it's not really a peer-to-peer file sharing. So yes, it is peer-to-peer and it shares stuff, but it's not file sharing. It is not centralized because it does not have a single point of failure. So there is no single element that you can shut down, which kind of shuts down the system. So it's not a centralized database. It is an append-only distributed ledger. And it is not a type of relational database. You don't have relations. It is sometimes, so the mechanism the blockchain shares the information is decentralized, but there is only one, yeah, it's a little bit like counterintuitive in a sense, but let me try to convey it. We will spend some time later on it as well. So if we consider Bitcoin, for example, if you consider a Bitcoin network as a network, it is a network of decentralized peers, and they kind of share information with one another, and they kind of form the ledger, the distributed ledger. The mechanism is decentralized. The distribution of data is there, but at the end of the day, there is like virtually a single database that they represent. There is like a single state of the world or state of the ledger. So there is only one ledger, right? And that means there is a form of centralization because it's only one ledger. So what could you have instead? So for example, if you, let's say you're building some form of system. Let's say you're building a system which stores credentials of people, right? So when you graduate, you get like a digital credentials, and you want to say that you have those credentials. So what you will do is you will kind of log a transaction in the ledger specifying that a particular credential has been created. So here, let's say we have a system. Let's have a decentralized system for credentials. Again, you have a peer-to-peer network of peers talking to one another, and then a credential is being issued. So you have like a document which is, I don't know, that Mariusz has a degree, like in computer science. I graduated with master degree, right? And then this credential is issued, but then we have to make sure that people can verify or validate that this happened. And this system does not have a blockchain. It does not use blockchain. It says, okay, we need to use something to kind of store that information, and it uses this blockchain instead and makes a transaction to the ledger saying, okay, that certificate with this hash has been created and now it's kind of sealed. So this hash is like logged in the ledger, right? So now a person who wants to verify, so now I get a credential, like Bob gets a credential from somebody with the hash. So there is like, I don't know, Alice, and she graduated from physical education, and she has the hash. And so, oh yeah, I need to verify that this credential is legit, that it is correct. So he needs to go here and check, okay, was it logged? Was this logged by this system? And if he finds it, he says, yep, that is legitimate credential because it has the particular transaction from that system and it's validated, right? But you can see that in this situation, in this use case, if this system goes down, it's a single point of failure, right? If this system goes down, then all this credential verification goes down as well. Like it's enough for one system to go down, for this system to go down. So, but this does not have one point of failure because you would have to shut down every single node in the network for this system to go down, right? So there is this duality, like, yes, there is only one ledger, but there is like n number of peers that you would have to take down all of them to actually kill the system, right? The system itself does not have a single point of failure, but it has this one ledger. And this sometimes it's a little bit like disadvantages, like you don't want to rely on a single ledger for your system because it may still present a certain risk factor, maybe a denial of service or some form of attack. So, but normally we don't consider Bitcoin as a centralized system, but blockchains typically do have just one ledger, which creates this sort of a single point of failure on some level. All right, so let's have a break. The first week is a little bit about like crypto systems. So it's what? Jesus. Sorry. I am a little bit, yeah, all right. So we kind of build up the prerequisites for talking about those things a little bit more in depth. Okay, so let's finish the slide deck and let's move on to some fundamentals of cryptography. So a blockchain is an open append only. Yeah, that's also an interesting concept. When Bitcoin happened, the concept of append only was known. We have append only locks. We have verifiable locks such that they lock something and they hash stuff such that you cannot manipulate your locks. So the append only was a known concept from before. But what Bitcoin changed is that there is a market for append only things. And IBM and others, they started offering like append only databases. So now you can, for example, have, so if you think about it, you can, what you can do is you can have an infrastructure provider, and IBM is like really hot on it, where you have a database. It's an SQL database, and it is append only, so you cannot change what is in there. And every time you put something in, you generate the state hash, and then you can sign it. So you can have like a private key where you sign the hash, and you kind of make sure that nobody can manipulate what is inside, because you sort of guarantee it. So if you have an organization, so if you have your organization with some PKI, do you know PKI? Public key infrastructure? We talk about it a bit later. So you have some mechanism of distributing keys and managing keys. Then in your organization, you don't need a blockchain. You can do like, you can say, okay, cloud provider, give me this. It's very cheap, and I will have the same properties as I have with the blockchain, but I will have this append only ledger done in a very cheap way. What I'm sacrificing is centralization, because now this PKI and this organization controls everything, right? But maybe that's what you want. Maybe you don't want to give up control, right? So for a lot of organizations, blockchains are not an answer because they don't want to give up control. They want to keep the control, and they want to keep the control centralized, but they can have all the benefits of append-only ledger. And then it's like in blockchains, we often say there is a, so if you say blockchain and you say it's an open blockchain, or it is like what's the name? Permissioned. And then the concept of permission blockchain is sort of does not actually make sense, because if you have a decentralized system where you're provisioning who can and who cannot write, then you can replace it, this complicated distributed and machinery, with something like this, which is much more manageable and cheaper, and you have exactly the same properties, right? So this became kind of a hot topic like 5 years ago or so. But over time, people understood, yeah, that makes no sense. I mean, we can just do the same with IBM. We have exactly the same security guarantees. IBM cannot manipulate anything because we have the security guarantees done kind of by us. And then we have a much cheaper and much more robust solution. So there are some kind of evolution of the concepts which happened over the years. And this is sort of interesting that we have this append-only kind of became reused in different situations. Okay, so next one. Boom. What is a, okay, have to start this one. It's, oh shit, it's the last quiz question. What is a genesis block? Yeah, it is the very, very first block. As I told you, like we're gonna go there next week, but as I told you, like it has to start somewhere, and then you have this sort of graph, and then you have your payment, like your last transaction, and then you have to trace it back. And then if you have a fake initial block, you can have a fake transaction giving you money, and you trace it back to this fake one, and it is legitimate. It kind of looks fine. So to prevent this happening, when Satoshi kind of released the initial block, he actually, or she, or the team, they used like a newspaper with the crash of the Lehman Brothers as a kind of proof that it was the real thing happened at that time. He did it, or she did it, or both, like the team did it, for two reasons. Why? To prove that whoever invented it didn't mind the coins before, so there were no coins mined up to that point. So it is really the first one, and so the time when it happened is actually the real time. So it was a particular date, and then the second reason is that they wanted to differentiate that block from any other block, so it has a special hash for that kind of a news item, right? So it's like authentic. Okay, did I click? Yeah, it does say which one was correct. Okay, so proof of work, a controversial property of some of the blockchains, including Bitcoin. It's not a quiz question, so you can take your time. So we're gonna learn about this next week. So you can get it wrong. No problem. So this one, validate transactions by staking crypto. It's called proof of stake. Proof of stake. in a proof of stake system, you become chosen to validate something because you staked crypto, right? In proof of work, it's different. It's not this one. Obviously, it's not this one. It's like a stupid destructor. Sign blocks with the private key. Private key of what? So we're gonna talk about signing and like verification. The correct answer is this one. So the correct answer is we have a block, and the block has some entries, some data, and it needs a hash, because then we're using that hash to make sure that the authenticity of all the blocks before it are correct. And we're checking it by checking the hash, that the hash is correct. And obviously we could take this data and hash it, like using some hashing algorithm. That's not a problem. This part, like we have to calculate the hash. This part is not a problem. The problem is that we want to prove that somebody burned time doing it, that they actually consume considerable amount of time and power to do this. So what we do is we say, yeah, calculating the hash is easy. What I want you to do is there is a special field called nouns, which is just a number. And I want you to manipulate this number in such a way that when you hash this, the whole thing, you're gonna get the hash that has a certain number of zeros up front. The more zeros I specify, the harder it is to find it, right? Because I have less possible collisions, right? So if I say, oh, I want you to have as many zeros, it's really hard to find a hash by manipulating this that has that many zeros, and then the hash kind of fits in here, but it has those zeros. So the number of zeros in the hash demonstrates how hard it was to find that collision, that kind of the hash that this is, that has this property, and you're doing it by manipulating this. You cannot manipulate this because that's what you're hashing, but you can manipulate that part, and together you're hashing the whole thing, and then you want that many zeros. So proof of work is this one. But we're gonna learn it next week in a bit more detail. So in crypto, are you familiar with some projects or some happenings or something that excites you or something that interests you? We will see how it goes. The interesting thing is that all of those are kind of, most of them is sort of money related, but we will learn about other things that are kind of not money related as well. Okay. So more requests. Where's my mouse? Right, so my mouse is here. Yep. All right. We will, so we will learn the foundations, which is that topic. We will learn about Bitcoin and Ethereum, which are those two topics. So those are all kind of foundational materials that we have to cover. And then we can go a little bit more into DeFi or a little bit more into Web3. Last year, we went a little bit more this way, and this year we probably will do the same because there is more interest. And it's sort of nice that you giving me the feedback here. So it's similar. So we will cover those three in the second and the last week. Okay, so what would you need to learn more about as a prerequisite? What do you think? from the slides that I was showing, what do you think you were sort of good at, and what you feel you would kind of need more? Yeah, so this is the topic which we'll start now. From the other topics, we will do some command line. Yeah, so maybe Linux and Bash might be good to have a refresher. We don't have to do too much of this. As I said, this is very nice to have, but it's not like really super important. It would make some of our life easier. And then this one, it depends. Like if we dive into Web3, then we have to deal with a little bit of REST and a little bit of JavaScript type programming. If we do a little bit more on DeFi, then dealing with the protocols usually is with some tools, like with wallets and like tools that are already pre-prepared. So this might be a little bit less important. Yeah, all right. Looks good. So what else would you like to learn? What else would you like to practice? Yeah, get rich quick. That's the hard one. Yeah. All right. So let's see how we did with the. So Eivind was leading and kind of finished number 1. Congratulations. Who is Eivind? Yeah, well done. Nice. So you will be tutoring others then if they have problems. Yeah, thanks for participating. What we will do now is I still need to talk. As I said, I prepared a little bit like this presentation and the next one. So I will start, and we will have a little bit more Q&A because it's a new material and some of it will be probably known to you. So what we can do is we can start, but I will tell you what to expect. So I didn't have access to Canvas, so I will kind of briefly outline what the first homework is. So the first homework is about keys, like RSA, for example, RSA keys for SSH, such that you can kind of log into a server without typing in your password. So SSH without password. Another one about keys is email. So you can generate a public-private key pair and be able to send and receive encrypted emails, right? So if we want to avoid taxes, we have to be able to communicate privately, right? Before tax office watching us. So like private public communication with encryption and signing, right? So for emails, for SSH. Then we need to know a little bit of crypto analysis, analytics. So we'll be cracking simple codes, right? So coding and cracking codes, such that we can estimate how hard certain things are and how easy certain things are and whether we can crack some things. I didn't plan to use like penetration tests or anything, like a little bit more on the theoretical side, but maybe we can do some password cracking, right? So maybe we can do that with the John the Ripper or something. Have you used this? Have you did some penetration tests already? All right, so maybe we will not do that if you already done that. But we will kind of crack some crypto systems. What else is coming? Let me just double check. So then we also have yeah, substitution ciphers. A little bit about crypto systems. Right. Yes. So OpenPGP for emails. OpenPGP. Yes. SSH keys for SSH server and for Git. Those of you who want to use Git. And then VirtualBox. So VirtualBox with Bash and SSH tunnels. So we want to be able to be somewhere and kind of bypass the firewalls and go outside or go from outside somewhere in, right? So using SSH tunnels to achieve this. It's kind of like you can use VPN using virtual tunnels over SSH. We will not build the entire network, just kind of a one-off thing, right? So this is what is, like, roughly speaking, what is the homework for this week. So the interesting bit is this one, because this one, which is what we will spend now some couple of slides on, right? All right. So then let me kill this one. Let me close this one. Okay. And crypto systems. We start with symmetric cryptography. Yes, I will post those slides into the canvas as soon as I can. All right. Right. Okay. Great. So we gonna talk about symmetric. We start today and we hopefully finish the slides tomorrow. But tomorrow we also do a little bit practical things. So we start about what are ciphers. Why do we need ciphers for? Why we talk about random numbers? And we do a little bit about crypto analysis, what sort of operations the crypto systems are using. And then we will talk about different modes of the symmetric and encryption, how the ciphers actually work. So we'll look a little bit inside. Some ciphers are quite complex, so you don't really need to like understand and memorize everything. Just kind of remember how they work. We don't really want to memorize too much We want to understand how they work and what sort of strengths and weaknesses they have, but you don't have to memorize like exactly how everything works. You can always look it up. But you should get a feel of the differences and why we're using one cipher over the other, where block ciphers are suitable and where they are not, and why we have stream ciphers, for example, right? All right, so yes, we have data which is not in transfer, and we have data that is in transfer. And in both cases, you know, bad things happen. So we have some examples. This one is the recent one from last year, where DeepSeek leaked a lot of chat history, which kind of involves people, personal information, and whatever they were chatting about with the bots, right? So it is potentially very highly sensitive. The leak was kind of stupid. So the stupidity was that the transfer of data was over insecure channel. So it was not encrypted. On the iOS, okay, I have it on the next slide. So on the iOS, it was encrypted, but in transfer it wasn't. And then in the iOS, the keys were baked into the binary as well. So if you have keys baked into binaries, you can always extract them and use them to decrypt whatever they were used for, right? So one of the principles of never to do it is to kind of bake keys into your binary. There's interesting kind of dilemma because I, for example, build like whatever, like if you build a tool, so if you build an app, so let's say you have an app, you've built an app, and your app talks to an LLM. So you have some sort of a LLM setup, and you have the auth token that is used to authenticate with the LLM provider, such that your app kind of provides this functionality, right? But you have to have this auth token somewhere, right? Because without it, you cannot talk to the provider. So here is the provider. And the provider kind of expects you to authenticate. And then you want your users to use your app, but your app is kind of doing something with LLM. So you have to have this auth token, right? So how can you deal with it? So if you violate the principle, you will kind of bake it in. But you should not bake it in, because if you bake it in, it will be extractable. So someone can extract it and use it and kind of, you know, make a huge bill for you, right? So what can you do if you have this situation? You've built an app, the app needs to talk to LLM, and then you have this sort of setup. What do you do? Yeah. Separate. Exactly. So what you need to do, you need to kind of set up a lightweight service. So some sort of service that the service stores the key. So the key is here. It is never in the binary. You distribute this, but instead of the app talking directly to the provider, the app talks to you, to your service, and you talk to the provider, and you kind of work as an intermediary, right? So then you can control the rate limits. You can control who actually can use the key, and who's like you can kind of authenticate or validate locally with the app, and then you never release the key out. Like it is something that needs to be kept private. So you keep it within your own infrastructure and your own service. So this is the kind of a default mechanism for dealing with this, not storing the key inside the app itself. So anyway, they did some bad things, and then a lot of like 1 million of logs were kind of snatched by the attackers because they didn't do encryption in communication. And also the encryption and storage was vulnerable. There is another one. This one is data in transit stolen. Similar situation. They were also not encrypting traffic, and the attackers hang around, like they found exploit, and they were hanging around in the infrastructure for like 3 months, and they collected like 8 terabytes of unencrypted data, about 25 millions of Americans last year. So ransomware group accessed the system for 3 months, extracted 8 terabytes of data, and a lot of personal information leaked. And some news agencies were calling it the largest data breach in US. Both of them are 2025. So for how long that has been going on? So I updated the slides recently. Before we used, before we use those slides, and this is data breach from stored data, which happened in 2009. So very similar story, like there is an organization storing something, whatever they are storing is not encrypted, and then they have an exploit, a vulnerability, and the attacker can get access to all the unencrypted data. And this one is very similar case, but with transmission. So Google admits like collecting Wi-Fi traffic, and it was basically like Google was the attacker, like exploiting the unencrypted traffic over Wi-Fi networks, right? So both cases, 2029 and 2010, were very old cases, but they kind of demonstrate that we have not learned our lesson. Like we know what not to do, but people still do the bad things, right? So what is the attack type? The attack type is that malicious actor gains access to the infrastructure or to the device, and the vulnerability is that once they gain access, there is no protection. The data is unencrypted, right? So a simple solution to kind of prevent those type of attacks is to make sure that your data is encrypted and the encryption keys are not stored in the same place, such that once a vulnerability is exploited and the attacker gains access, it gains access to the encrypted data, not to the plain text data, right? Or when they observe the traffic, they observe encrypted traffic, not non-encrypted traffic. So kind of encryption is the keyword here, right? So some terminology such that we always use and understand the same terms. So plain text is always the original message. It's the one which is not encrypted. Ciphertext is the encrypted message. And then encipher or encrypt is the process of encoding it to the ciphertext. And decipher or decrypt is the reverse. And cipher is the algorithm for converting plain text to ciphertext. And the key is a sequence of symbols, which is used to describe how this is done, like what is actually like how the transformation is performed. And this key is like the essence of where the security comes from. The security comes from the key. The more random it is and the longer it is, the better are the properties of the encryption. So it's a very schematic view. We have plain text, we have the encryption, we transmit the ciphertext, and then we decrypt. And the key is the same key. If it's a symmetric cryptography system, the key on this step and this step is the same. So nothing kind of unusual here. Everything pretty simple, right? Any questions so far? I think it's like pretty straightforward. So if we have this, very simple system. So I have a message. So let's say I have a plain text M, my message, and I encode it as bits. So I have some sort of a sequence of bits, right? And it finishes with 3 ones, okay? So this is my message. And then I come up with a extremely random sequence of bits again, and I will call it my one-time pad, right? So I will call it one-time pad, another sequence of digits, which is like, I cannot do randomness myself, but let's imagine that there is some sort of a random sequence. And this is my key. It's the random sequence of the length of the message. And then I use XOR. Do you know XOR function? Exclusive OR. So XOR function is like this. If you have X, which can be 0 or 1, and you have Y, which can be, how to draw it? Okay. So I have X can be 0 or 1, and Y can be 0 and 1. So then 0 with 0, and we doing XOR. So 0 with 0 is 0, and 1 with 1 is 0, and 0 with 1 is 1, and 1 with 0 is 1. Okay? So here I have my X, and here I have my Y, and I'm doing X XOR Y, exclusive OR function. So 0 with 0 will give me 0, 1 with 1 will give me 0, and if I have the opposing ones, I get 1, right? So then if I calculate this, I would say, okay, this is 1, this is 1, this is 0, this is what? What is this one? 1, this one? 0. Okay, so you got it. So now if I do this, and I have my ciphertext, so this is my ciphertext, right? And I go backwards using the same one-time pad, look what happens. 1 with 0, 1 with 1, 0. 0 with 1, 1. 1 with 1, 0. So I can reconstruct my original message, right? So by doing XOR this way or this way, I can encode and decode the plain text into ciphertext, right? Extremely simple mechanism. And if I tell you that this is the best encryption that can potentially exist, would you believe me? We cannot get more secure than this. Never. This is the ultimate secure system. Okay? It has problems though. One problem is that the length of the key has to be the same as the length of the message. So if you need to encrypt 1 terabyte of data, before sending it, you have to have 1 terabyte of key, and you have to generate it first, right? So the key has to be the length of the message. The second problem is you have to securely communicate the key for every message with the recipient every single time, right? So let's say you want to transmit 1 gigabyte of data. You generated this. You have to give that 1 gig of key first to the recipient. Then you can send your encrypted data, right? So those two properties are already quite hard. And the third one is this has to be random, like actually properly random, which is expensive as well, right? So we have 3 properties of this OTP system, which makes it a little bit impractical. why we cannot beat this? Why this is the best that can happen?
Is it because the key is only used once?
Yes, because the key is only used once, and because so if you think about it, I have a certain number of content, right? And I convoluted it. So this is my message. This is my plain text, and I convoluted it with a complete randomness, right? So I have this, and I convoluted it with the complete randomness. So on the exit, on my ciphertext, what do I have? Complete randomness, right? So here I have randomness. And now if I want to crack it, if I want to say, okay, what this randomness leads to, I have to try out all possible combinations of that 2 to the power of that length keys, right? I can crack it. Like if the message is very short, of course I can crack it, but it takes me to try out all possible combinations, right? And then if the message is quite long, then it becomes kind of more and more impossible for me to go over all possible combinations. And the possible combinations grow exponentially, right? Because it's like the power of 2. So like with the length, it goes like very quickly through the roof, right? So for very short messages, I can brute force it, but for bigger messages, I can try to brute force it, but brute forcing it becomes kind of unfeasible for us. We have a slide later to see how long it may take to brute force certain lengths of keys, right? And then there is no property because this is random. This is random. I cannot reuse any tricks, or I cannot reuse any like insider knowledge of how this has been generated, because it is truly random, like sequence. So and none of the cryptoanalytics methods will work on it, right? That's why we say OTP is actually ultimate crypto system, because it doesn't have any properties. It is actually random, statistically completely random. But we cannot use it, like because it is impractical to use in normal situations. So we have to have something else. But this sort of bitwise convolution of randomness with our messages actually, like, we cannot beat it. Like, there is nothing better than this. So why we sacrifice this let's say perfect crypto system? For multiple reasons. One reason is we want to encode really big message, like big message with relatively short keys, right? I want this one to be gigabytes, but I want this one to be 212 or 512 or 2048 bits of key, right? I want the key to be like relatively short compared to the message, right? But if I have relatively short key relative to the message, you can see I already have cycle, right? I already here will observe a certain cyclic behavior because my key has to be repeated like over the bigger data. So there are some properties within here that I can exploit. I can try to analyze statistically. So the length of the key is one reason. The second reason is we generally don't like symmetric cryptography because it relies on me sharing the key with somebody in a secret way, right? But because I want to share something with somebody in a secret way, saying, yeah, you can do it, but you need to have a secret way to share something with somebody, it's like defeats the purpose, because that's the problem I'm solving in the first place, right? If I already have a mechanism to securely share something with somebody, why do I need this, right? So symmetric key cryptography is like shooting yourself in the foot a little bit. Like, we really like asymmetric. And then the last one is the requirement of this being like really random is a little bit hard. Like we usually go with pseudorandom, and it's good enough. So theoretically, there is nothing that can beat this, but in practice, we cannot use it. It's only a theoretical limit. All right, so what we can assume. So when we like we have different situations when the attacker is trying to uncover whatever the real message is, and we can make a certain assumptions. So there are, like, if we assume that the attacker only knows the ciphertext, we have a certain certain properties, right? So we are assuming the attacker only knows ciphertext. What would be the definition of a perfect secrecy? That the attacker cannot recover the secret key or the plaintext. And the ciphertext should reveal no information about the plaintext. What can you tell me? Like, what do you think is the ultimate goal? Like, what would define a perfect privacy? So this one is a little bit like maybe kind of not clearly formulated, because if the attacker only knows ciphertext and the attacker can recover plaintext, does that mean that they recovered the key or not? So if I have a certain ciphertext, and hypothetically, a person comes back and says, yeah, that ciphertext means, I don't know, Mariusz is lecturing, okay? It kind of deciphered it. Can I assume that the person who knows the plaintext also knows the key or not? So who thinks yes and who thinks no? Yeah, you think that the person knows the key. Yeah. Who thinks the person may not know the key? Yeah, why? Yeah. Yeah. That's right. So it is possible that you can like decipher something, but don't know, like, so let me show it. So you have message 1, message 2, message 3, message 4. And then you have plain text. This is plain text. So plain text and ciphertext. So ciphertext 1, ciphertext 2, cipher 3, cipher 4. And then a person was given this and they discovered this. Does that mean they know the key which is used for all those possibilities or only for that single one? So, or do they don't know the key yet? Like, let's say they don't know the full key, but they were able to do, as he was saying, to do some analysis of the ciphertext and some properties and recover some of the plaintext and then fill in the gaps themselves. So they are not sure 100% that this plaintext is actually correct, but it looks correct from the guessing, right? So that is possible. It is possible that, like, the cryptanalysis gave them, like, you know, those competitions where you have some letters and you have to guess what is there, and you guessed what is there, but you don't know the key, right? It is possible. So you can do some analysis, get some information, and then fill in the gaps and find out this, but you don't know the key. And then you have to do the same process for this. If you know the key, then you know kind of all those transformations, right? You can kind of do it for all the transformations. So so if the attacker cannot recover the secret key or all the plain text, is it perfect secrecy? Or is the ciphertext should reveal no information about the plain text? So which one is stronger? The second one, yes. So the first one says, okay, we have a ciphertext, and by doing the cryptanalysis, we can guess some letters, and then we can fill in the rest. And that's kind of not perfect secrecy, right? Because it leaks, this leaks some information that is recoverable. It does not leak the key, but it leaks something, right? And then the second one says, no, we cannot even do that. Like we cannot even guess stuff, right? So then it's stronger. So this one is a stronger condition. And then an encryption schema is computationally secure if the cost of breaking the cipher exceeds the value of the encrypted information, or the time required to break the cipher exceeds the useful time of the information. Both are true and both are used, right? So can you have an encryption schema that is computationally perfectly secure, that it will never be broken? Can you have that? No. So that's not possible, right? Like you always have a limit, but if you put the limit beyond the lifetime of the information or beyond the costs of the value of the information, then we say yes, it's computationally secure, because it does not make sense to be breaking it anymore, right? So it is a little bit maybe breaking hard, because that means no matter what we do, no matter how hard we work, we cannot really have a perfect computational privacy, right? The privacy is just a matter of time, which is also interesting because, for example, police has a lot of evidence in their locker rooms, like mobile phones, hard drives, encrypted hard drives, a lot of evidence, and they just wait and wait. And then suddenly SHA-1 was broken or something is broken, and they say, oh, great, let's open it again. And then they can decrypt it, right? And let's open the case. With mobile phones, it's even more dangerous because operating systems and everything has vulnerabilities and exploits which are discovered later. And then once it is discovered, they say, oh, great, now we can break in. Like we have this exploit we can use to break in. So it's just a matter of time, right? Some things you can design in such a way that takes very long time to break. But still, you know, it is never is perfect. So random numbers. Do you know John von Neumann? John von Neumann is a guy who invented sequential processing. So like Alan Turing was the guy who invented calculus for like how to do computations. And this guy made it actually practical. Like he invented a machine which could be implemented to do this calculus. So the calculus was more like a mathematical concept. And he kind of is the father of the von Neumann architecture. Like how our computers work is basically what he designed. So he was a very smart guy. And he said, if you consider arithmetical methods as producing random digits, you're doing it wrong, because it cannot be random. It's never random. It's predictable, right? Properties that random number generators should have is that they are statistically random. They have uniform distribution and are independent. So when you observe the sequence, they have those properties. And then they should be unpredictable from the previous values. So if you observe it, you cannot work out what will be the next value. and it cannot be reproduced. So this means pseudo-random generator, or the ones which are arithmetically produced, don't have those properties. So one property that real random number generators have is if you observe the sequence, there is never a cycle, like it never repeats itself or never kind of repeats the same sequence, right? But with pseudo-random number generators, at some point it will start repeating the numbers again. It can be a long sequence, but it kind of always goes to the limit and then kind of wraps around, right? A real random number will always produce numbers. It's sort of like the extension of pi, right? So if you go extension of pi, this sequence never repeats itself. It's actually truly random, right? But it cannot be reproduced. And of course you can reproduce it, like, because you know it's a pi, right? And you cannot predict future values from previous one. Of course I can predict what is the 10th digit of pi, right? So even though it has the first property that it doesn't have a cycle, it is truly random, the distribution of digits is random, it's very nice. It's not a good pseudo-random number generator because I can predict, I can calculate what the extension of pi is, right? And then we use pseudo-random number generators and randomness in cryptography in a lot of places. So we use it for nonces, we use it for session keys, public generation, and so on, and for one-time paths in key streams. So there is a lot of places where we really need a proper randomness. Otherwise, the system will collapse, right? So there is an interesting case. So there is an interesting case where, without going into all the details, there is this concept of zero knowledge proofs, ZKP, zero knowledge proof. Have you heard about it? I will probably spend some time on this next week because it's a very cool concept. But without going into details, what it is that you have a certain box that allows you to do certain things without revealing other things. I know it sounds like kind of blah blah blah, but you kind of you have a box which allows you to prove certain things that they are correct without somebody revealing to you what the value is. So let's say I have a certain secret. So Mariusz knows a secret, and you tell me, no, you don't know that secret. And I tell you, yeah, I know that secret. And you say, prove it to me. So then what I can do is I can use this box and I can use my secret and I produce a proof to you that you can verify. And then by verifying this proof, you are certain that I know that secret without you learning what that secret is. So you don't learn what that secret is, but I can prove to you that I know the secret, right? So anyway, I will go into that like later. What I wanted to say is we need this box, right? And to construct this box, you need to use a little bit of random numbers, which are later disposed. You have to delete them. Okay, so when I'm creating this box, I can use those random numbers and then I can delete them, and then I have this secure box. So there is a cryptocurrency called Zcash. Zcash is very secure. It uses zero knowledge proofs for the transaction checking. So it checks that the transactions that is happening in the blockchain is correct, and it doesn't leak information. So it is very private. It's more private than Bitcoin because it hides all the details about the transactions, but it needs this box. So Zcash needs this box. And when the developers were building it, they said, oh, we have this problem, because to get this box, we need to have those random numbers. And then if someone has those random numbers, they can cheat. And this verification thing doesn't work anymore, because they have an insight of how the box works from those random numbers. So then they can generate proofs of things that should not be provable, right? You get the idea. So they can break the system, right? So the developers said, okay, when we are building this box, we need to have those random numbers, but we also have to have a way to dispose it. So they developed a clever mechanism where they use a group of people. So there was like a group of people, each of them generating random numbers, and they had like a protocol of combining those numbers in such a way that none of those people could know what the other person numbers were into a number which was subsequently used to build this box. And even though those people know the individual numbers, there is nobody who knew all the numbers to produce the box. Only the protocol knew. And then even though they have it and they might not have deleted it, but they should, that is unusable unless all of them collude. If all of them collude, then it will break the system. But if one of them does not collude, then it will not break the system and the box is secure. So Zcash relies on this like secure box out of the group of people, and you always wonder, did they collude or not? Like now Zcash is worth much more and there is more incentive to cheat, but is all of them going to cheat? Like, did they store the waste, the zero knowledge proof waste or not, right? So it's kind of a social dilemma, like how, and so far we have no evidence for them to cheat. Like it looks, Zcash is working fine. It has all the properties that it should have. The secure box is secure, and all the zero knowledge proof waste was actually properly deleted, right? So it looks like a very nice experiment. Yeah, so we do need those random numbers in many places. So then we have the pseudo random number generator. And then it is a deterministic algorithm to create something that looks like random numbers, but they are not truly random. The output fulfills the properties of a random number, and that's those properties which we had here. Statistically random, uniform distribution, and independent, right? Those are the properties. And pseudo-random number generator does that, but it does not do this, because it does that as well. So if you know the sequence, so if you have number 1, number 2, number 3, number 4, there is infinite number of possibilities of what. No, it's not infinite. It's kind of contained. Yeah, this is a very nice problem of how you calculate complexity and how you calculate space in computation. So there is a very nice metric called Kolmogorov complexity. Kolmogorov. I think they spell it with K. Kolmogorov. This guy said, okay, if I have a sequence of ASCII characters, if I have a sequence of, I don't know, A, B, C, A, B, C, A, B, C, and it goes to infinity, how complex is that sequence? It's quite simple. It's just A, B, C in a loop, and it goes on, right? How difficult is the pi? Well, it also goes to infinity, but it's kind of quite straightforward to write a program which outputs that. So he said a complexity of the sequence is worth the smallest program, the shortest program that can generate that sequence, right? So a truly random sequence, a sequence which never repeats itself and goes on forever, and it's truly random, would require a program that is as long, because there is no way you can produce it shorter than the length itself, right? So a truly random sequence is very complex using Kolmorogov complexity because the program is as long as the sequence. Any other sequence is shorter, but if your program is longer required for the sequence, that means the complexity is larger, right? So you can have a sequence of numbers, and then that complexity, if let's say you have a particular sequence of numbers, and then you have another sequence of numbers, you can use this complexity measure to see which one is more complex, which one requires a longer program to generate it, right? So this property here means that if you see the numbers, you cannot predict what will be the next number, but that would mean if you see the numbers, you would have to guess what is the program behind those numbers to be able to calculate the next number, right? And normally it is not possible. And normally the program also needs a seed. So that even though you may guess the algorithm, and many algorithms are public, so you can check, oh, is it this algorithm or is it that algorithm? You still need to know what was the initial seed used to generate that sequence, right? So you have to kind of brute force here. So even if you knew the algorithm, you still need to brute force here to find the seed. And if the seed is like, 64-bit integers, you have exponential growth on checking brute forcing this, right? So we cannot do that. And then it cannot be reproduced. So this one can be reproduced. If you have the seed and if you have the algorithm, then you can reproduce the sequence. So with the pseudo random number generators, we have this one property which is missing, which is that you they are pseudo random and they can be broken. And many exploits, many vulnerabilities are because people obtain the randomness to something that they should not obtain, and then they crack something. All right. So if I have a source of true randomness, then my output is truly random. If I have a seed and I have a deterministic algorithm, then I have a pseudo-random bit of strings. And then if I have additional parameter, if I have additional context, I have something like this, but with additional thing that kind of wraps around. And then I have a pseudo-random value. So we have kind of like three different things. One is like the perfect one. So like some source of true randomness, which is just encoded into a random bit stream. This one is a bit stream as well, but it starts with the seed and then goes on. And this one is like a clockwise, kind of like a tickwise. So you have a tick, and then you're saying, okay, there is a seed, there is a context-specific value, and then you're calculating the next value, and you feed it back here, and then you're creating like one value at the time. And this is like a pseudo-random value instead of pseudo-random number generator, right? So the properties of those stream-based and the one which creates the value are slightly different. And this one is kind of differs by this extra context that it has. So you have the true random number generator, pseudo-random number generator, or pseudo-random number function, which kind of ticks and generates a value. These ones are, you can say, yeah, this is also a function. It generates a bit at a time, but you're not really interested in the bit. You're interested in the combination of bits. All right. Yeah, so the last one is just one value, not a stream. These two are giving you streams. Yeah, so this is all we talked about already: uniform distribution, independent, unpredictable, and backwards unpredictable. Okay, so back to one-time pad. It has a perfect secrecy. It is very fast, but it's not practical. It requires very big keys, and so on. So where it can be used? When do you think one-time paths can be used? So every time we have a kind of a situation where we have a contained block, which is like if our message is much bigger, but we cut it into blocks, and then each block we kind of cipher with the path, but we don't generate that path for every block. We sort of generate it once and then modify it based on some cyclic properties. We could use it. So we can use it for block ciphers. Okay, one more definition. So cryptography is the study for storing and transmitting data. So cryptography is like the study of the algorithms of how we can transmit and store information such that it is protected. And then cryptanalysis is the breaking of the systems. So it's like the science of studying what properties, like what are the cycles or properties that we can exploit and breaking them. And then cryptology is both. So cryptology focuses on cryptography and cryptanalysis. Again, like people get confused. They often confuse the cryptology with the cryptography, and sometimes mean cryptography when they really mean like breaking the codes, and that's cryptoanalysis. So analysis is analyzing the systems, cryptography is designing the systems, and cryptology is like doing both, like designing them and then checking what vulnerabilities they have and modifying them and so on. It's like a cycle. All right, so then we have various systems, and we have like various ways of making the encryptions. And this is a list of different ways of changing the plain text into ciphertext. And the simplest one is substitution. So Caesar cipher is a cipher where you have the alphabet, let's say A, B, C, D, and then you make a shift. So let's say you want to write Abba. So you want to say Abba, but if you say, okay, I'm using a cipher which shifts everything 3 letters right, then A will be D, A, B, C, D, E, F, right? So then you have a mapping, and the mapping is A becomes D, B becomes E, C becomes F, and so on. And then it drops around such that like the last letter of alphabet becomes like the first one, or like not really, like you have to shift it, right? So it will be like shifted. So the last letter will be, because we're shifting by 3, we started here, so the last letter will be C, right? And then the previous letter will be will be B and A. So then if you want to write this text, plain text, you would say D, E, D, E, right? It's a very simple crypto system using substitution, substitution of the original letters with the ones shifted. And then this is the ciphertext, and to recover it back, you have to like map it back. So you have this like, this mapping becomes like the key. So the key actually is like, the key is 3 because we're doing the shift, right? So substitution replaces characters. Transposition rearranges the bits. So we will see some examples in a moment. And then product ciphers kind of combine substitution and transposition. The substitution can be really simple, like this one, where we say, okay, shift everything kind of right, but you can have a substitution which has this sort of a table. Let me show you. Table-like mapping. This one I think is not this. Yeah, let me see this one. So this one is like a typical, yeah, so you can see that the plain and cipher follows the sequence. It's like D, E, F, G, H. So that means it's a Caesar cipher, right? If this are kind of random letters in random order, that will be a normal substitution cipher, and then this would become the key, because you need to know which letters map to which letters, right? But because it is in sequence, you only need to know how much they are shifted, right? Does it make sense? Yeah. Okay, so transposition is a little bit different. In transposition, let me see if I have this right. No. Okay, so in transposition, we do a little bit differently. So we can do this example. Let's say we say lazy, and let's use 1, 2, 3, 4, 5 columns. So lazy fox jump. Okay. So we say lazy fox jump, and then we do some filler characters. Okay, we kind of fill it with something, fill it with, let's say, X's. Okay, so now this is our plain text, and we do transposition. So we're gonna reproduce it by reading columns first. So we're gonna write it this way: LOP AXE ZJD YUX and FMX. Okay, so now this is my ciphertext. I didn't substitute any letters. It is the same letters mean the same letters. I just rearranged them in a different sequence, right? So now to recover it, you need to know like how many columns did I have originally, right? Because if you know how many columns I had and how many rows I have, then you can kind of know how to read it, right? So if you know, okay, there are like 3 rows, so you have to jump every 3. So it's like lazy F and then 1, 2, 3. So 1, 2 fox, right? And then G, and then so on. You get the idea, right? So to decipher it, I need to know how the matrix look like, and then by knowing that it has 3 rows, I can kind of unpack it. But if you don't know it, it's like a lot of permutations. You would kind of have to rearrange letters in different ways to sort of be able to decipher it. So this is a transposition cipher. So substitution is always easy in a sense of mapping letters to symbols or some other letters, right? Either letters, or you can use hexadecimal characters or something. Like it kind of messes up the character set. Unless you're using like a Caesar cipher where you're using actually letters as well. With this one, it's always the same alphabet. It's always the same letters, but you just kind of rearrange it. So that's the difference between substitution and transposition. And surprisingly, all algorithms, all known algorithms, they use combination of those 2 techniques. There is nothing else. It's like just this plus some bitwise operations like XOR and things like that, that form crypto systems. So there is no real magic. It's kind of this or this. I mean, and usually combination of those 2 operations. So we will see later, like the concrete algorithms, how they do it and how they use those two mechanisms to achieve the complexity that it makes them difficult for crypto analysis, right? Okay, so single key, symmetric cipher, two keys, asymmetric cipher. We already covered that. And then the way in which plaintext is processed, block ciphers. So in block cipher, we have a message and we take it as a whole and we produce the outcome, right? How practical is that? Where would you do this? Where would you use a block cipher? Okay, so maybe it's a little bit, maybe I confused you. So if I have a message, this is my message, right? If I have the key, which is of the length of the message, then I have the OTP case. And we know this is impractical because our messages typically are quite long. Even an email, right? Can be like a couple of pages long or whatever. Then do I need the key that long? So normally what we do is we split the message into blocks. So we say, okay, I split it into blocks. And then my key is of the size of the block. So where, like, imagine that we have disk files. We have a movie on a disk. We have email with attachments. Would you use block cipher for all of those?
What's the last one?
Email with attachment.
Oh.
So this is a block cipher. A block cipher takes the content, splits it into blocks, and then encrypts each block using the certain key, and then produces the cipher text or cipher text, right? So if this is like my file, then this is my encrypted file. So this is block. The alternative is you don't split it into blocks. So this is your message. And then what you do is you say, okay, I will take 1 byte at a time. I will start reading it. So I will read the message. I will encrypt the byte. I will produce the byte, and I will keep reading and producing 1 byte at a time. So I will do kind of a stream of output, right? So it's like I'm reading it, and as I read it, I kind of encrypt like byte size, and then I produce byte outcome, and I kind of produce the stream. So this one is similar, but you're sort of operating on the stream instead on the blocks. So when would you use this, and when would you use this?
The last one for streaming audio.
Yeah, exactly. That's how, like, the name gives it away, right? Every time where you have the mechanism where you're kind of streaming something, where you're passing data through something, and you don't really deal with a file or kind of a giant ciphertext encrypted artifact, you would use this. Every time you sort of want to encrypt the file, you would use this. Why? Could you use this to encrypt the file? Could you read a file like 1 byte at a time, encrypt it, and then store it? Would you do that? Yeah, you could do it, but why don't you want to do this?
You get incomplete information.
No, you can read all the bytes. But why this is not something you want to do? Yeah, I guess it might be a little bit confusing, but if I have 1 gigabyte of something and I need to pass it over the network, right? What will happen if I encrypt it here, then pass it over the network? You see what happens? Like I'm spending a lot of time first without sending anything, and then I'm sending stuff while I don't do anything anymore. I like my CPU is not used and my IO is used. But in the first phase, my CPU is used a lot, but my IO is not used at all, right? So it's an imbalance. It's like inefficient. So if you need to send something over the network, it's better to do a little bit and start sending it. While I'm sending it, I'm doing this next bit and so on. So I'm kind of like, and also the person or the end, let's say it's an audio or film, starts getting it while I didn't finish yet. It's like it's streaming situation, right? But if I am on my hard drive and I need to convert 1 terabyte or 1 gigabyte of file into an encrypted format, and I do it 1 byte at a time, it's very inefficient, like reading. Like you want to read big chunks, you want to read the buffer, right? Have you tried like copying a file like 1 byte at a time to a new file? You can write a program, right? You can try it. You can try like how long it takes to copy a 1 gigabyte file if you're reading it like 1 byte at a time, or if you read it like 500 megs at a time. You read like poof into RAM and poof back to disk, right? It's super fast. Like if you do big buffer, right? If you do like small, it's super inefficient. So this one for disk and storage is very inefficient. You can do it, but it's very inefficient. This one you can do for network, but it's also inefficient. Like you don't get the benefits of doing IO while you're processing. So they have the use cases. The use case here is like local storage and files. The use here is the streaming. Yep.
So let's say I'm downloading a movie legally.
Yeah. Obviously. Yeah. Yes. No. So the way it works is this. Well, I think we will have slides after actually. So if like on the entry, you have a long movie, right? This is a long movie, and let's say we're reading from let's read from here to here. So I'm reading the first part, I'm encrypting it, and I'm pushing it through the network, and you getting it. You're getting the first block, right? Before, like, and this is secure. Secure. Like I encrypted it, and you have the key, right? So you had the key for the first one, and then when you got it, you decrypt it, and you can show it to yourself or whatever, right? So the streaming is secure, but I'm doing it 1 by 1, and you kind of getting it 1 by 1. But after each one, you can already decrypt that part and start using it, and so on and so on and so on, right? I don't use the same key all the time, because if I use the same key all the time, a person who was the malicious actor and was observing it would eventually learn the pattern. So by reusing the key and like doing the changing of the data all the time, they would kind of get the cryptanalysis going and will say, oh yeah, I can see some patterns, I can crack the key. That's how web is cracked. So you know web?
Wi-Fi?
Yeah, for Wi-Fi. You can have a cracker, and you can have like a mobile station, observe traffic long enough, especially if someone sends a long file, and crack the key for web protection. That's why web is not advisable to use, because anybody can sort of crack you, because they just observe long enough, get the statistical properties and crack you, right? So what the proper ciphers do, they introduce additional information, like for example, like the sequence number or something extra. So each block, each like byte has a slightly different key, and it is like changing. So it's like changing, but the core starts at the same point. So you would have to crack the first one to be able to crack the rest. But if you haven't cracked the first one, then you know the next one is as hard as the first one because every time it's different. Yeah. So you don't wait for the whole transmission to do something with it. You can do it on chunks. Here you cannot. Here you get the block. The block is encrypted, and then you get the block, the buffer encrypted, but you need to get the rest of the file if you want to do something with it, like if you want to decrypt it or something. Again, you have to do it like per block. Yeah. Okay, so block ciphers and stream ciphers, you can use them interchangeably, but they don't both fit the same situations. You want to know which one fits a given situation better. So local storage, mostly block ciphers. Network and streaming, stream ciphers. All right. I think we should have a break. And tomorrow we're gonna go into those historical ciphers and some modern ones. And we're gonna look inside how they work. I already showed you how Cesar worked today, but we will see some other ones, and we will see some of the modern algorithms that are used, and look a little bit inside how they do it.